used to, and be more about telling you stories and features of different tools that can help you, and help you do what? Well, effectively realize that the threat model in the software environment has evolved over the last years pretty quickly. Quick slide on me. My name is Louis Jacomet. I work for Gradle, where I'm mostly on the dependency management and JVM team. And so I've participated in some of the developments we're going to see here. And that's pretty much. If you want to know a bit more about Gradle, get some t-shirts, stickers, we've got a booth down there in the exhibition area, so you're welcome to visit us after the talk. So it's been, and there have been a number of examples showing that a supply chain attack against development of an application, of a set of applications, is no longer an hypothesis. I mean, there have been stories out there of companies getting infected because they installed an infected version of a software and all of that. And this is, while it could be something that people could reason about in the past, it's been shown to be a reality. And for example, a couple years back, two sets of attacks were really close to each other, like the CCleaner and the Asus tools update. Effectively, what happened is that hackers managed to compromise the auto-update functionality of an application or a series of tools that you install on your laptop. They hacked that update system, through the update, install a backdoor, collected information on the impacted systems, and when we talk impacted systems, the CCleaner attack was about 6 million devices, just to give you an idea. From that information, they then performed targeted attacks to dozens of devices. So they effectively started something to get a large number of people infected in order to get access to a few critical systems. One of the linked attack to that, because it has a similar execution plan, was the Microsoft tools attack. So same initial pattern, through a few targeted attacks, they managed to compromise a series of tools for development. These tools were then used by game companies that signed the binaries they produced. The problem was not the signature. The signature was valid, performed by the games company, no abuse there. However, the shipped software was not the software they thought they were building. It contained packages, exfiltration systems that would then leak information and allow attackers to go deeper into the networks of the targeted users. So this is, of course, something that you might react to saying, well, all these closed source folks, they had it coming, open source is way better. Well, somebody did an experiment. A number of people, especially when you use a Mac, use Homebrew, which is effectively the missing package manager for macOS. At least that's their tagline. And when you use such a tool, what you do is you update a tool based on the Git repositories that then links you to a number of packages that you can install and everything. And one guy, Eric Holmes, in 2018, wanted to see if he could attack such a system. And what he found out was that in 30 minutes, he managed to commit something on one of their main repositories. Why? He looked at the project. The project has a Jenkins instance running their builds to show everything is running, everything is fine, and then promoting the latest changes to their master branch. Except that one of their Jenkins instances was leaking their API, their GitHub API key into the system environment. And when you've got a public Jenkins instance, if you don't pay attention, that system environment, it's just a link on the left-hand side of the build. That's what he clicked, got that key, realized that the key gave him tons of access, submitted a commit, and the commit was accepted by the system. I mean, he's using a valid legal key. Of course, he didn't profit from that. What he did was a responsible disclosure to the managers of Homebrew, which reacted promptly, verified that the key wasn't used to do malicious actions on the repository throughout its history with the help of GitHub. But that's the kind of thing, you see that open source is not a magic answer for that kind of context. Then a colleague of ours took a look at all the security advisories against JavaScript projects. And he found out that nearly a quarter of them are for intentionally malicious packages. meaning this is not a bug, this is not a buffer overflow, this is not a mistake in the programming. This is a package that's been transformed explicitly for doing bad things when it gets installed. The Ruby world. At some point, RubyGem's package repository found out that 11 Ruby libraries had been infected and deployed as pseudo-official packages. And what the packages were doing, well, they were mining cryptocurrency whenever you ended up using them. Again, all of these problems, you could say, are, well, you know, this is the JavaScript world. I mean, these folks are crazy. You add a JavaScript dependency and you get 80 more packages coming in. And you remember like stories around the left pad package that suddenly got pulled and you've got builds failing all over the planet because suddenly you're missing that critical element. Well, maybe not critical, but you don't realize that you're actually needing it. And again, we're all, or at least you're all mostly Java developer. I'm a Java developer, and you could say, that's not our problem. I mean, we control dependencies, right? Wrong. That's a real dependency graph. Okay, it's a large application, I admit, but still. And it's zoomed out so you can't recognize the names or anything, but that gives you an idea of the complexity of making sure that none of these is poisoned. And sadly, some are. A guy decides to do some Android proof of concept with audio features. And he finds a project on GitHub that has 1,000 stars, and it's pretty much recording and playing audio as an Android library. He says, oh, that's perfect for me. How does it get into my project? Well, use Jetpack. Jetpack, if you don't know, is a service that allows you to depend on the binary of a library that is not published. It will effectively take the GitHub project, build it, and then make that available to you. So you no longer go through the publishing process of Maven Central or other repositories like that. You can directly depend on what's built from master. The problem is the moment he tries his app, the app crashes because it's trying to do internet access. And it didn't give internet permission to the app because it should not need them. I mean, it's a standalone app for recording voice and stuff. And when looking at the code, he finds that the library picked is actually sending all his phone's data to a server by doing a remote call. He's like, that's weird. When I go look in the code source on GitHub, that code isn't there. So it's clearly a difference between the code source and the package binary. Removes the dependency to Jetpack, code still compiles and everything, meaning the dependency is actually not the one he was expecting. It's not coming from Jetpack. As it happens, somebody had seen that project, had seen the 1,000 stars, knows about the Android ecosystem where effectively JCenter and the Google repositories are added first as repositories to fetch dependencies from. And what the bad person did was simply publish his own version of the library to JCenter, abusing the artifact ID, so the group ID and artifact ID of the original library. And because JCenter is first in your repositories, that's what you get. And so really, one of the big changes that has happened over the last years is that hackers don't necessarily attack your network, your database directly anymore. If they want to get to you, they might use means such as I've presented, which means they might attack one of your software supplier so that through what seems like a legit update, you actually get poisoned code running inside your infrastructure. And from there, they'll keep digging, starting to do whatever they wanted to do. Encrypt all your things and ask for money, or exfiltrate data. And of course, these kind of attacks are not only practical. We've seen some examples where they're clearly done by individuals. Then you can imagine what a nation-state actor, if he really wants to go at a company, can do with that kind of things. So that's a scary setting. Now, we're still building application. That's not going to stop anywhere anytime soon. So what can we do? Well, if you think about the application building, there are a number of entry points in there. The first one is new code. If you build an enterprise internal-only application, you should say, yep, that's pretty safe for me. But if you build an open source library, well, potentially anyone can start opening pull requests. Then there is the whole CI infrastructure. Can bad things happen on CI? Then there is, of course, the dependencies. We've discussed some of that. The repositories. We've shown one example where it was the repository doing the wrong thing. If you use a build tool like Maven or Gradle, you've got plugins, but pretty much any build tool around has ways of being extended so that you can do more things with them. Then, of course, you've got the tools themselves. Is the binary distribution of Maven or Gradle that you're using the right one, or is it also used as a way to inject code? I mean, you can even go further, right? You could have the compiler being the problem. And then, of course, sometimes you end up with local file system issues, which pretty much means game over, because at that point, if attackers have access to your local file system, you can't do much. And then you realize, and we'll discuss some of that, that sometimes you add services, and some of these services actually stem from good ideas, but they open up extra attack vectors. And so that's, for example, one thing you've got with build cache. So let's look at an attitude to adopt towards new code, and especially when you think about your CI infrastructure. If you've got an open source project, that's an easy way. I mean, if your open source project effectively builds all pull requests without question, you're taking a risk, especially if you're building it on your own CI infrastructure. You've got people that offer such services, Circle CI and others, and effectively what they do is they take all of that responsibility on their side, because what you could do is anyone starts, bit mining, I mean, crypto money and everything of that. And so the thing you want to do there is make sure that you pay attention. But not only that, you've got another variant, which is you see a pull request, it doesn't get automatically built. But as a developer, as a committer on the project, you get it locally and you build it locally, which could even be worse, because then you've compromised your own machine. And so, in a way, you should never try out PRs. What you should do is look at all the files. And that includes, if you look at GitHub, the ones that they collapse, oh, this is a too big a diff, I'm not gonna show it to you. Yeah, you want. Please show it to me. Don't try to run things, and pay extra attention to the things that are not direct. Oh, he changed the URL to a package repository. Oh, he updated a tool version, meaning we're gonna download a new tool version. Or he updated a tool version and added an extra repository. Like, does the real tool effectively exist at that version, or will it be magically found only on that new repository that you know nothing about? So you can, of course, use a number of systems like contributor license agreements, meaning that you've got at least an idea of who's behind the pull request, checking the background of the person, like is it someone that's suddenly randomly opening tons of PRs across multiple projects and always saying, oh yeah, go to the latest, and then nothing else. Review first, of course, and if you really want to run it and you're still somewhat unsure, well, one of the things we're doing now is using isolated, disposable build agents, because then at least everything is self-contained. Another thing, of course, is signing the commits. Who's aware that with Git, you can change the author of a commit on the command line? Okay, so that's good. The others, that's a reality. Git, the author information is just metadata, and you can set that metadata to anything you want. And so if I want to commit using the name of one of my colleagues or using the name of a contributor to the project, this is just a command line thing to do. When I push the information, if I've got write access to the repository, it looks like it's coming from him. It doesn't look like it's coming from me. Behind the scene, of course, somebody acquired a connection to the repo to push the commit, so that might be used if the connection is authenticated to a person and not to a token. But otherwise, it looks like a legit commit from a colleague, except it's not. If you don't have write access and you're starting to open pull requests, well then, from a fork, then of course it means you've got deeper impact on the whole scheme of things. But that's the kind of possibility with Git. However, if you start signing your commit, then you add cryptographically secure information to the commit, which is again one level higher. And of course, that means also that you need to check the key and that you need to revoke keys when they get leaked and all of that kind of problem. So it is a defense, but it comes with a number of drawbacks as well. So there is always that balance in security between convenience and effectively being secured. On the CI level, well, disposable containers, like we said. However, disposable containers are really a pain for performance. Both Maven and Gradle downloads, I mean, the joke is Maven is downloading half the world, Gradle does the same. If you've got tons of dependency and you run that build on a fresh host, the first thing it's gonna do is download tons of stuff. What is a disposable CI container? It's a fresh host each and every time. And also, when you're using that kind of a system, well, suddenly, potentially, a vulnerability on the host might be the thing that gets people in. So again, compromise. So one thing that Gradle offers as a performance mitigation solution is the build cache. And with the build cache, the logic is that something that has been built, like compiled or tests run on one machine, is then uploaded to a cache, can be reused by another build, and so effectively you win back some time that way. You remember at the beginning I had mentioned that introducing a build cache introduces other issue. We'll get back to that. Of course, the build cache makes it possible to reuse task output, but you need the secure connection, and it doesn't deal with the dependency downloads we've discussed. What you can do there is potentially copy or share a dependency cache, which is something that the latest Gradle versions, 6.1 and 6.2, allow you to do. But still, you've done something for security, and now you've got a performance problem to resolve, and some of the ways you're going to resolve that performance problem opens up new security problems. Then if we look at dependencies, plugins, and the repositories they're fetched from, who here is using either Maven Central or JCenter as a way of pulling third-party dependencies in their project? Okay. And of those, who is using them directly versus having like a proxy in between a Nexus or an Artifactory instance? So who goes directly to Maven Central? Okay, so less people. Okay. So all of the binaries that are on Maven Central, JCenter, and others have some security or at least authenticity capabilities associated with them, except that a number of them are kind of outdated. So MD5, it's been known to be insecure for a long time. SHA-1 was known to be not secure, not fully secured anymore, but recently research have shown that it is now possible to use a given filling so that you can produce a jar that will end up having the same signature as the jar you're targeting. So the attack became non-theoretical but practical. It still requires a lot of computing power, so you would still need somebody who's really dedicated to use that system, but it means that effectively SHA-1 is really no longer secure. And signature files that you find on Maven Central, for example, it also depends on how they're produced. What are you signing exactly? If you're signing the MD5 or the SHA-1 checksum of the jar, you're back to the same problem. What you're signing is actually not fully secure. So with checksums, what you get is integrity. Okay? However, if the integrity information is collocated with the binary you're trying to download, guess what? If I'm an attacker and I manage to change the binary, will I leave a file with 50 characters that allows you to know that I changed the binary? I'll probably change that file as well. So ideally, what you want to do is use the checksum from a different source. Go back to the project that published the jar, and hopefully they list the checksums. And if they don't, that's probably a good request to make for the project so that you can verify that what was published, that what you're getting is what they announced as published. Since Gradle 6, what we've added is that when you publish with Gradle 6, we will do also the SHA-256 and SHA-512 files, so that we are more future-proof in terms of having a checksum that proves the integrity of what we produced. But again, if the file only exists on the repository where you upload, it can be changed alongside with the binary file if an attacker gets access to that server. Another thing is that Maven Central now has a process for verifying what you're uploading. But at the start, that was not the case, and some binaries made it there, and their checksums don't match. So aside from knowing that this binary and its checksum don't match, what do you know? Nothing. It was published 10 years ago. It might be hard to just track down the source code, and even if you track it down, maybe it's going to be hard to build it because of the Java version required and all that kind of things. JCenter is in a way clearer. It doesn't take the upload. If you want the MD5 or the Chawa checksum, it's going to compute them from the archive it's serving you. So really, the only guarantee it gives you is that what you asked from the server is what you got locally, nothing else. You can sign artifacts, and I would recommend doing so, especially for open source things that you hope a lot of people are going to use. What that does, though, is prove the origin. Uses PGP, meaning for checking it, you need some tools, you need some knowledge, it's not always easy. I mean, again, convenience gets hurt there. Worse than that, sometimes you will lose your key. That means that suddenly up to version 154, you were signing with a given key, and 156 is signed with a different key. How do you explain that? Sometimes, sadly, what happens is that the private key gets stolen, and then you've got someone out there that can sign your packages, except they're not your packages anymore. And also, like I said, because the signature file uses checksums as well, if the checksum itself can be compromised, then the signature remains valid because what you signed was the checksum. So that's one of the reasons we decided to add a feature for verifying dependencies within Gradle. And so with Gradle 6.2, who's going to be released soon, the first release candidate was on Monday, you'll have the ability to create a file which is going to use XML, and that file will effectively allow you to record the public keys you trust, checksums that you trust if there is no signatures, for all the binaries that are coming inside your Gradle build. And all the binaries means not only the dependencies of your compile and runtime class path, but also the plugins you're using. Because with an extensible tool like Gradle, attacking through a plugin allows you to do pretty much anything. You're inside the same JVM, you can do whatever you want. You get access to the file system and all of that. It will not only also check the binaries, but it will also verify the metadata. Because that's another vector of attack. Instead of changing the binary, you add dependencies. And all these tools are great. They will fetch the transitive dependency graph of your dependencies for you, which is amazing. It's a nice feature. That's how you get 80 package per JS JavaScript dependency. That's how you get the dependency graph I showed for a Java application. It's really convenient, but again, in terms of security, it is kind of scary. And so here, you'll make sure that also the metadata was the expected metadata. And of course, because you want some convenience, you'll be able to generate the first version of that file. If you do that, please verify what it has generated. Take a look inside the file and make sure that the different checksum, the different keys you're starting to trust are effectively the right ones. Maven has similar support, mostly through external plugins, which makes it a little bit more limited in terms of scope. So for example, it will only cover the dependencies, not really the plugins, or at least not as an integrated fashion. And it will mostly, the plugins that exist will mostly verify the binaries, the jars. The thing, though, is that we took that dependency verification feature and applied it on the Gradle build tool's own build. and it started failing. I mean, a developer created the first version of the file, did the work of verifying that everything makes sense, then it gets sent to CI, and boom, different version of a dependency. And when I mean different version, I mean different jar. I mean different metadata with different dependencies. And that's where you realize that what you're running locally, where you don't have the CI infrastructure, so you don't go through a proxy repository and you effectively hit like JCenter and Maven Central directly, produces a build which is slightly different than the one running on CI, because that one goes through a proxy, and the proxy sometimes, for historical reason, maybe for internal bugs, whatever, ended up picking the same jar, so same coordinates, except that it's not the exact same one. It has a slightly different checksum. Or a jar that suddenly has metadata, like you find an artifact on Maven Central, it says, I have no dependency. You look on JCenter, and it has a POM file with dependencies listed. What? And so clearly, that's a problem. We already have a consistency problem, so we had to do all kind of tricks, verify that we were building the same thing, getting the dependencies from the same places so that we could have a single verification file. And for a couple artifacts, we actually trust multiple checksums. Because otherwise, depending on your local setup, you end up picking the other one, and yeah, they're binary equivalent. I mean, they are programmatically equivalent. They will do the same thing, except that they were not produced at the same time, little changes in timestamps, different signature. Now, we've discussed one of the examples where actually the problem is the repository act as malicious. That package published to JCenter, which was squatting the name of a legit package and adding a bit of code in it. Bintray used to allow that. They've now reinforced the security around that, so they will ask you to check that you own the namespace you're trying to deploy to, which I think is a good thing. But clearly, that's a potential problem. And that's, of course, what's stored on the repository manager. But then you had all the man-in-the-middle attacks. When you're downloading dependencies, up to recently, you could hit Maven Central, you could hit JCenter on HTTP, meaning that your binary dependencies could be replaced on the fly. The good news is, and I didn't do a big fix on that slide, but the good news is this is over. And people probably got a couple builds failing on the 16th of January and the days after that, because really a number of repositories stopped accepting HTTP requests. Gradle was one of them, Maven Central, JCenter, and others. So it was a coordinated effort that took a long time. There were a couple of tryouts, but effectively you no longer have HTTP access. You cannot download a binary that is then used by your code through HTTP. And then you've got newcomers on the block. GitHub had a great idea. Hey, look, we're going to make it super easy for you to produce your own binaries. Attach to your GitHub account will give you a repository. And go ahead, put things in there. Well, the thing is, it's your own repository. So you put whatever you want. Welcome, squatting packages and the like. The good thing is that for now, the feature requires authenticated access, meaning that it's a conscious decision to add it inside your own build, because not only will you have to reference the repository, but you also have to get credentials for it. When you do that, please go look into the repo. What is there? Is there only the dependency you expect and nothing else? If not, well, maybe don't add it and find another way to get to the binary. One of the bad things that Maven does in that sense is, in Maven, if you get a dependency and the dependency happens to declare repositories, Maven will happily use these extra repositories to resolve dependencies. It is a great convenient feature. It means that if you do a Maven plugin, for example, and your Maven plugin requires dedicated libraries, you don't have to tell the users, oh, by the way, get my plugin, but also please add that repository to your configuration. No, you just add the plugin, and by downloading the plugin, Maven suddenly has a new world of repositories to fetch binaries from. In security, aspect, this is a catastrophic thing, because effectively it allows you to potentially, again, shadow legitimate packages with hacked version of them. That's one of the reasons that Gradle offers repository filtering. So what you do there is you actually select per repository which packages you're allowed to download from. It is not only safe, but it also potentially is a confidentiality aspect. If you talk to the people maintaining Maven Central or JCenter, they will tell you they know about most of your secret projects. Because if your repositories are not in the right order, you will send a query asking for my company secret project 1 version 152. Are you there? No, I'm not there, but that's a logged request. And with the company ID and the project, well, sometimes, you might deduce things there. So this feature got enhanced in Gradle's, or is it coming in 6.2? 6.1 or 6.2, sorry, with something that allows you to effectively do exclusive resolution. And so what you can say is, here you see you can include groups, exclude stuff, but then pretty much if you want to make sure it only is found in JCenter, you've got to exclude it explicitly from all the other places. And so the added feature is effectively a richer DSL, which allows you to say, oh, for my company packages, it's exclusively in my internal repo. And so you do that only at a single place. And even if you add later an extra repo, there is no risk of forgetting to forbid that dependencies to be downloaded from there. It will be automatically done by the tool. Here, we've got a nice benefit as well, which potentially you're improving performance because we're looking for dependencies only where we're supposed to find them. So that's the help. For example, when you do dynamic version dependency, so you use a range or you use a plus notation in Gradle, which allows you to say effectively, I want any version in the 1 dot range. Gradle will go over all the repositories. Because historically, we've seen and we've had requests from users that, well, we were deploying versions 1 to 1.2 on that repo, but starting from 1.3, we decided to use another one. And so we end up looking across all of them. So here, by restricting that, you're also helping these kind of requests to be more constrained. Now, we've looked at a number of things, but when you think about dependencies, one of the main aspects of dependency is that their life cycle doesn't end at publication time. You discover bugs. Sure, then you do a bug fix release. Can you let people know that they should upgrade? Another problem is somebody actually figures out a security vulnerability in the dependency. What can you do then? And the problem is also that potentially bad metadata is published. You've got a dependency in there, it shouldn't be there. And that means you potentially are increasing the number of binary jars that you find on your class path for no good reason. But that increase can lead to more bugs, more security advisories, and the like. So one of the things you can do with Gradle is you can actually use rich version declaration. And so here what you see is that we're using commons compress. However, we want the version to be strictly from 1.0 to 2.0 excluded. If nobody has an opinion, let's use 1.19, because that's what we built with, that's what we tested with. However, what's really clear is that 1.15, 1.16, 1.17, and 1.18 should not be used. They have a CVE. That information, of course, can be added in your build file. However, what happens after a while is that you're potentially not touching that version. You don't want to go back to touching that thing, and so it might allow those versions. Well, Gradle offers you the ability to enrich the metadata or your dependency declaration when it sees them, and so you can dynamically add that kind of thing. And so what we have is we've got a couple of customers that have larger code base, thousands of developers and the like, and what they do is they've got internal plugins that will effectively enhance the metadata based on a description file. And what happens is that when they realize, oh, there is a new CVE, they just add the exclude there, and then transparently, it effectively starts applying to all of their projects. And yes, it potentially breaks some projects, because you're saying, 1.18 as a CVE, and there is a project out there that was relying on a specific behavior of 1.18, and they tried with a version before, they tried with a version after, didn't work. Constraint. Well, at least your build fails, and you know you've got to address the problem. So we've looked at code, CI, dependencies. But like I've said, there is also the tooling. And so, for example, one of the things we've added with Gradle is we've started publishing the checksums of the Gradle wrappers and of the full Gradle distribution. And the wrapper task itself, or when it downloads a new Gradle version, because you've upgraded the wrapper, will verify if you've added the distribution SHA into your Gradle.properties, into your Gradle wrapper.properties, it will effectively verify that the version you're downloading is the right one, is the correct one for that given version. And here you see the exact example of the binaries live on a server where you download them from, and the signatures live on the documentation, which are different servers. Sure, you could still compromise both of them, but it means it's a larger scale attack. It's even more issues. Another thing we've done is we've added a Gradle wrapper GitHub action. So GitHub actions are effectively part of the new offering that GitHub gives you, where you can start having a workflow on every pull request, every push to master, and the like. And the action we've done is, well, if anyone in your Gradle projects is nice and say, hey, take that new Gradle wrapper, it's a better version, like I'm upgrading the latest Gradle wrapper, but Gradle wrapper uses a jar, like you've got a binaries checked in. Well, that action will check that this binary is actually a legit binary coming from Gradle, and not, again, something that someone tried to have you use because it's a Java app that you're going to run on your local machine, meaning it will probably have all of your developer access, which most often the case is administrator access, effectively. And so that's easy to add on projects. There is a few tricks with the different billing plans of GitHub. Like if you're a free user, it's not a problem, but if you've got a legacy billing plan, some of these actions are not available. But aside from that, if you've got a Gradle project out there, that's a good recommendation to add. One of the issues we have with Gradle is that we have a number of third-party distributions that exist out there. So first of all, there are a number of Gradle official Docker images. Well, they're official in the sense that they use an official version of Gradle, we hope, but they're not official in the sense that they're produced by the Gradle team. Debian systems and other Linux systems have a tendency to rebuild everything from source. The problem is they effectively build from their own source, into which they do cherry picking of fixes while still pretending they're the official Gradle release. And so often you will see like GitHub issues on the Gradle issue tracker being filed about, hey, look, Gradle is doing that. And then we ask them, can you run Gradle version? And even though it says 564, the checksum of the commit doesn't match, it doesn't print the same information, and we know then, sorry, I mean, get an official release and try again, and if the problem persists, we can discuss, but otherwise, we can't maintain this rebuilt version. And at the same time, I understand in a way why they do it, right? We'll talk about that in a moment. So please, please, when you use tools, and I think the same stands for Maven, make sure that you're using the official version and verify that the version is indeed untampered with. So I'm going back to the external services, which is part of that whole tooling aspect. So the Gradle build cache is amazing for performance. Really, really amazing. If you want to know more, come to the booth. But it's also a security risk. Suddenly, you've got a place in your infrastructure where, based on a key, we will upload compilation results. And then if anyone else in your organization that has access to the build cache attempts to build the same stuff instead of compiling, it will get the results out of the build cache. That's where the performance gain comes from. Well, if you manage to poison that entry by having a different output, you've infected potentially all the developers that end up pulling from the cache. So clearly, protect the access to such features. Make sure that the write access is limited to the minimal number of people that need it. Of course, in order to leverage that kind of attack, you need to write a custom client, so it's not an easy attack, but it still is a possibility. And in a way, that leads to the whole concept of making sure that your builds are reproducible. If from the same Git commit, you manage to use 2 different installations, like completely separate installations, and produce the exact same binaries, byte for byte, then you know at least that either you were like completely screwed because both lines were effectively corrupted the same way, or at least you know you've produced something that seems to make sense. But then it means that in builds, you've got issues when you're using features like dynamic dependencies. Sometimes you don't realize, but you've got undeclared inputs, like you'll take the time of the build and put it somewhere in some files. That's the timestamp stuff. You even have issues with potential compiler bugs. If you don't have the exact same version and there is a compiler bug that's triggered by your code, boom, you've got different outputs. I think Groovy suffered from such a bug at some versions. Like compiling the same code would generate, compiling the same source file would generate the same code binary-wise. However, the method orders were different. They were not consistent. Well, that still gives you a different byte-for-byte output. Then you've got the Apache Software Foundation. Their motto is source only. So effectively, the binaries for any Apache project that you find are just convenience. Otherwise, internally, they rebuild everything, and they have their own version of the binaries to make sure that you only use stuff that they've built, implying that they trust their own CI infrastructure for doing that. And so effectively, they're telling you, well, if you want trust, build from sources. Because then it's between you and your tooling. We gave you the source are visible. If you want a binary you can trust, we recommend building from source. The problem, of course, is if you try to do that in a medium-sized company with a huge dependency graph, you'll have to build a whole lot of things. And especially whenever you want to upgrade a dependency, it becomes a completely different process. Google, of course, just said, well, we'll have a single repo and everything is sources. They operate at a different scale. It's not something I would recommend to try out as a company. It poses different kind of challenges. But in a way, it's safer. So clearly, one of the things that happen is that you have to make compromises around security. But if we manage to get to a state where, for example, an Apache project had binaries produced by some big names company, and they could prove that it was the same binary produced by another big name company, then you've got full reproducibility, and you could start creating a web of trust. Like, oh, look, all these folks are producing the same binary from the same source. I bet that's the correct one. In the sense of providing that kind of reproducibility, Gradle has a number of features. So one of them is dependency locking, meaning you can have the benefit of easy upgrades via dynamic dependencies, but you still record what was the resolved result at a given point in time. Meaning that if someone later reruns that same build and newer version of the dependencies existed, they'll be ignored. The checksum verification we've discussed, that already helps as well, because if you verify that this build with these dependencies, with all these checksums, produces that output, then at least people that are trying to reproduce the same things can validate that they effectively have the same dependencies. And then, of course, on all the archive tasks that you find in Gradle, you've got methods and we've got documentation to explain to you, hey, here are the things to tweak so that you get a reproducible archive. So ignore timestamp, make sure we've got always the same ordering and that kind of things. So what I wanted to give you with this talk is really an idea that not only such attacks are now possible, but we all run in a crazy and safe environment in a way. With all the tools we're using, with all the dependencies we're implicitly trusting. So there are tools out there to help you, but as you've seen, we've discussed a number of steps. And if you think with the mindset of an attacker, there were still gaps in between those steps. So really, be aware, that's the first thing. Decide how much security you or your organization needs, and then start applying patterns, features, leveraging tools. Thank you for your time. I welcome any questions. I think we've got a couple minutes left. I leave up, when I share the slides, I've got a couple references, and most of the stories I told have articles reference. And if you're interested in Gradle and developer productivity engineering, Hans Doctor will be doing a talk later today due to a schedule change. So please check it out. And if you've got questions. Okay. Oh, yeah. Yes, yeah, I will publish the slides. Yes. I don't think that's a question. No. Okay, well, thank you for your time. Enjoy the conference.